Imagine you have a microcontroller sitting right there on your bench, and it's just silently, inexplicably failing.
Oh, the absolute worst.
Right, like you've checked your C code 100 times, you've run the static analysis, the logic is, flawless, it compiles perfectly. But the second you flash it onto the physical silicon, it just completely ghosts you.
Yeah, you get nothing.
Exactly, nothing. The display is blank, the serial port is dead, and the chip itself is essentially just sitting there hiding a secret. So welcome to today's deep dive. Today, we're looking at how embedded systems engineers are basically completely abandoning the idea of trusting their source code.
Which sounds crazy, but it's true.
It does sound crazy. But instead of trusting the code, they're using tools like the new Regmon 2.0 console to, well, mind read the hardware directly. Our mission for you today is to break down exactly how this non-invasive silicon inspection works, specifically through the 4 major new features in version 2.0.0.
Yeah, and it's this massive paradigm shift in embedded development. Because historically, when you hit that wall where the software says one thing and the hardware does another, you just enter this diagnostic wasteland.
You're completely stuck.
Right. You start relying on like print statements or blinking LEDs, or you pull out the logic analyzers, which require you to physically solder these tiny microscopic wires to the pins.
Which nobody wants to do.
Nobody. So what we're exploring today is this concept of non-invasive hardware silicon inspection. It's the ability to interrogate the physical truth of the chip without actually altering its behavior in any way.
And to really grasp how revolutionary this new version 2.0 of the Regmon console is, we kind of have to establish the baseline first, right? Like the diagnostic tools that came before it. We're talking about a tool that acts as a live register monitor for ARM microcontrollers, and it communicates over the serial wire debug, or SWD, interface.
Yeah, the SWD.
So for the engineers listening, you probably already know those 2 tiny wires, SWDIO for the data, and SWCLK for the clock. That is our physical bridge into the chip.
Right, and in version 1.0 of Regmon, that bridge was used in a very specific, I guess you could call it a somewhat naive way.
Naive how?
Well, it would connect over those 2 wires and perform these blind memory reads to fetch live register values. But raw hexadecimal values are pretty much useless to a human, right? So to make sense of them, version 1.0 relied entirely on an SVD file.
A system view description database.
Exactly. These are these massive XML documents that silicon vendors like STMicroelectronics provide, and they map out every single peripheral, every register, and every bit field to a very specific memory address.
So it's basically the topographical map of the silicon.
That's a great way to put it, yeah.
It tells the software, like, hey, the control register for the UART serial port is located exactly at memory address 0x40001000.
Right.
And once the tool knows that, it can translate that, hexadecimal soup into a plain English human-readable readout. It even had a local AI acting as an assistant to help you interpret the bit flags.
Which was incredibly useful. But it had this glaring, almost fatal flaw if you were doing iterative workbench development. It entirely trusted the human operator.
Which is always a mistake.
Always a mistake.
Right.
Version 1.0 came preloaded with a single SVD database based on whatever you told it to load. It just assumed that you, the engineer, knew with absolute 100% certainty exactly which chip you had plugged into your ST-Link probe.
Which, that sounds completely reasonable until you actually look at a real engineer's work.
Yeah, it's a disaster zone.
It is never just one pristine board. It's this messy pile of STM32 F1s, maybe some FDZO and L4 prototypes from 3 months ago, mixed up with revisions from yesterday. And if you plugged, say, an F0 chip into Regmon 1.0, but the software was actively loaded with the F1 mapping file,
You get a catastrophic misalignment.
it's reading the wrong memory addresses entirely, right?
Yes. Because the memory map for an F0 is fundamentally structurally different from an F1. But the software, it doesn't know that. It just executes the memory read whoever address that wrong XML file gave it.
So it gets garbage data.
Exactly. It gets whatever random data happens to be living at that wrong address, and it confidently displays it on your screen as if it's the UART control register.
It's a total mapping disaster. It's kind of like navigating a network using a Wireshark capture from an entirely different subnet. You're looking at the packet payloads and you're confidently diagnosing a TCP window issue, but you're actually just looking at like raw, unformatted audio data from a completely different server.
Right. You are debugging your code against a physical reality that literally does not exist.
And that just leads to hours or even days of chasing phantom bugs. I mean, you're sitting there rewriting your serial drivers because the tool is telling you the port is configured incorrectly, but the port is actually fine.
Your tool's just straight up lying to you because you fit it the wrong context.
Which brings us to the overarching philosophy of version 2.0.0. Here's where it gets really interesting. The developers realize that relying on human memory for hardware configuration is a massive bottleneck. So instead of forcing the human to guess, Regmon 2.0.0 interrogates the silicon itself to find the absolute truth.
It shifts from being just a passive monitor into an active reverse engineering workbench.
And the first major mechanism they use to achieve this is a feature called detect chip. Let's break that down.
Sure. So Detect Chip elegantly solves this whole mapping disaster by leveraging the ARM core site debug architecture. Inside pretty much every modern ARM microcontroller, there's a dedicated debug unit. It's known as the DBG MCU.
Okay, the debug microcontroller unit.
Right. And baked directly into this unit is a read-only register called the ID code.
And just to clarify for everyone, this isn't in the flash memory, right? This isn't some setting a developer can accidentally overwrite when they flash a bad program.
No, not at all. This is physically burned into the silicon during the manufacturing process. It is a permanent, immutable 32-bit serial number, and it contains these very specific bit fields for the version, the part number, and the manufacturer.
So it irrefutably identifies the exact chip family.
Exactly. It basically tells the SWD probe, I am physically an STM32L0x2.
So when you initiate the detect chip function in the new UI, Regmon sends a request over those SWD clock and data lines we talked about. It bypasses the main CPU core entirely. It accesses the core site ROM table, traverses the debug bus, and just extracts that ID code.
Precisely. It grabs the ID, parses the part number out of it, and this is the really crucial automation step. It uses that physical ID as a hash key to instantly fetch the exact correct SVD database for that specific piece of silicon.
It effectively ends the guessing game completely.
Completely. I mean, for an engineer who is rapidly prototyping across a bunch of different hardware families, this just eliminates all that setup friction. You unplug a cable from an F1 board, you plug it into an F4 board, you hit detect chip, and within literally 2 seconds, the software's topographical map is perfectly synced to the physical reality of the silicon sitting in front of you.
No configuration menus, no drop-downs.
No human error.
Okay, I love the automation's brilliant. But I do have a little bit of pushback here on the actual diagnostic value of this.
Okay, let's hear it.
Well, knowing the chip family, pulling the right SVD file, that really just gives us the architectural blueprint, right? It tells us what peripherals could exist on the die. But it doesn't tell us a single thing about what the chip is actually doing dynamically in that moment.
That's true.
Like, knowing a server has a gigabit network card installed doesn't tell me if it's currently dropping packets under a DDoS attack. So how do we transition from just knowing the static hardware mapping to actually understanding the live execution behavior?
That is the exact limitation the developers sought to overcome with the second major feature in 2.0.0, which is called Analyse Reg. Because you're entirely right, reading a register value once, which is what most traditional monitors do, it's just a static snapshot.
Right. If you pull a status register one time, you get a 32-bit hex value representing that exact microsecond in time.
And in the context of embedded systems, a microsecond snapshot is virtually useless for diagnosing timing issues or complex state machines.
Why is that?
Well, if you look at a single frame of a Wireshark capture, you can see a flag is set, sure. But you have absolutely no idea if that flag just flipped, or if it's been stuck there for an hour, or if it's rapidly toggling up and down as part of a high-speed data transfer.
Oh, I see. So Analyse Reg introduces the dimension of time into the tool.
Exactly.
Yeah.
When you target a specific register with Analyse Reg, the tool initiates this high-frequency polling sequence over the debug link. Instead of one read, it grabs 20 consecutive readings of that exact memory address, spread evenly over a period of about 10 seconds.
So it's actively building a time series dataset of the hardware's state transitions.
Yes. It watches the specific bit fields within that register to see how they mutate over time, and then it hands that entire time series packet over to the local AI to perform pattern recognition.
Okay, let's ground this in a real-world engineering problem for a second. How does this time series analysis actually catch a silent firmware error that a normal, traditional debugger would miss?
Let's look at serial communication. Say you have a UART transmitting telemetry data. One of the most common things in engineer monitors is the UART status register, specifically a bit called the TXE flag.
Transmit data register empty?
Right. If that bit is a 1, it means the hardware buffer is empty, and it's ready to accept the next byte of data from your C code.
Makes sense. So if it's a 0, the buffer is currently full and it's actively shifting data out on the physical transmit pin.
Correct. Now imagine your system is locking up. The serial output just stops. You use a traditional debugger, you halt the core, or you take a single snapshot read of that status register, and you see the TXE bit as a 0-way. What do you think?
My immediate conclusion as a developer is going to be that the peripheral is hung. Like, my code shoved a byte into the buffer, the hardware somehow failed to transmit it, the buffer is full, and my whole state machine is just deadlocked waiting for it to empty.
Exactly. You see that 0-way, and you immediately blame the hardware, or maybe you blame your clock configuration. But the physical reality might be that your serial port is running perfectly fine, maybe at 115,200 baud, and your single snapshot just happened to mathematically align with the exact microsecond the hardware was shifting a byte out.
Of course. It's the aliasing problem. I sampled at the absolute worst possible moment.
Yes, you caught it mid-stride. But with Analyse Reg, you aren't taking one snapshot. You're sampling 20 times over 10 seconds. If that UART is actually healthy and actively moving a stream of data, the AI looks at the time series and it doesn't just see a flat 0. It sees the bit toggling, 0, 1, 0.
What detects the actual heartbeat of the peripheral?
It sees the motion, yeah. The AI processes that statistical variance and can confidently tell the engineer, look, the peripheral is not hung, the TXE flag is actively mutating, the hardware is alive and moving data. It completely reframes your diagnostic approach.
That is incredibly powerful. It differentiates a permanently stuck state from a highly active state, which, like you said, are basically indistinguishable if you just take a single snapshot.
Right.
But this is targeted at a single register. Modern microcontrollers, like the STM32H7, they have hundreds of peripherals and thousands of registers. I cannot realistically sit at my bench clicking Analyze Reg on every single memory address. It would take a week just to profile the chip.
Which is precisely why Analyse Reg is really just the foundational mechanic for the third and, frankly, most ambitious feature of Regmon 2.0.0.
Which is?
Analyse Prog, or Analyse Program.
Ah, okay. This is the mind-reading feature.
It is. If Analyse Reg asks the question, what is this one specific bit doing? Okay, Analyse Prog asks, what is the entire macroscopic architecture of the software currently running on this silicon?
Okay, I have to challenge this right away, because to map the entire dynamic state of every peripheral on a modern ARM chip, that would require an immense amount of polling over a relatively slow SWD link.
Yeah.
The bus contention alone would be massive. How does it optimize this so it doesn't take an hour to run a single scan?
That's the trick. It doesn't scan everything. It uses a highly optimized traversal algorithm that exploits the fundamental power architecture of embedded systems.
Oh, okay. How so?
And starts at the RCC, the reset, and clock control unit.
Ah, the master clock gating.
Exactly. In an ARM Cortex-M system, you do not supply power and clock signals to peripherals you aren't actively using. If your code doesn't use the analog to digital converter, that piece of silicon is physically unclocked. It's essentially dead space.
Right, you have to explicitly enable it in the AHB or APB bus enabled registers, otherwise it draws zero power to save battery.
So Analyse Prog doesn't waste bandwidth pulling thousands of dead registers. It goes straight to the RCC. It reads those specific bus-enabled registers, the AHB-NR and APB-NR, and instantly computes a bit mask of exactly which peripherals are actually receiving clock signals.
It checks the breaker box to see which rooms have power, and then it just prunes the rest of the silicon out of the search tree immediately. That's a massive big O optimization.
It cuts the search space down by like 90% in milliseconds.
Wow.
Then, for the peripherals that are alive, it initiates a bifurcated scan. First, it reads the static configuration registers. These are things like baud rate prescalers or GPIO mode registers that are set once during initialization and basically never change.
So it gathers the static architectural topology first.
Right. And second, it initiates a wide net version of Analyse Reg across all the dynamic status registers of just those active peripherals. It samples the counters, the data registers, and the interrupt flags repeatedly to capture the system's kinetic energy.
So it knows what's turned on, it knows how it's configured, and it knows what's actively moving. It builds a complete system-wide dynamic fingerprint.
And then it hands this massive complex matrix of static topologies and dynamic state changes straight over to the local AI.
Okay, and this is where I need to really dig into the mechanics with you, because reading the source material, this part sounds like pure science fiction. You are handing the AI a giant CSV file of hexadecimal states and timing variances. How on earth does it correlate a bunch of random hardware flags to the actual software intent without ever having access to the C source code?
It's fascinating. Let's use the thermometer example from the field reports we looked at,
Yeah.
because it perfectly illustrates the heuristic matching the AI is actually performing here.
Okay, set the scene.
An engineer is running an unknown binary on a board. They have no idea what the code is. They run Analyse Prog. The tool reaches over the SWD wires, queries the RCC, finds the active peripherals, samples their states, and feeds that raw hex matrix to the AI.
And the AI has zero context. It doesn't know it's looking at a thermometer.
Now, it's completely blind to the application. But the AI looks at the data and applies architectural heuristics. It says, okay, I see the timer 2 is active, and its CNT, its main counter register, is rapidly incrementing in a non-linear fashion. I also see that SPI1, which is a high-speed serial bus, has its data register being continuously loaded, and its transmit flags are toggling. Finally, I see specific pins on GPIO port A are configured as outputs, and they're toggling in sync with the SPI traffic.
Okay, so a human engineer looking at that raw data would have to spend, what, an hour cross-referencing data sheets to figure out what that specific combination of states means.
At least an hour, yeah.
Yeah.
But the AI correlates it instantly. It synthesizes those disparate hardware behaviors and outputs a plain English architectural deduction. It basically says, based on the hardware telemetry, this system is running a timer-driven input capture, likely reading a pulse width sensor, and is simultaneously driving a continuous data stream out over an SPI bus, utilizing GPIOs for chip select lines. Conclusion: it is a sensor-driven display loop.
It completely reverse engineered the intent of the compiled C code sensor in, display out just by observing the wake it leaves in the hardware registers.
Yes, it reconstructs the software architecture entirely from the hardware's exhaust fumes.
That is just mind-bending. But wait, here is the absolute most critical part of this entire operation. We're talking about reading hundreds of registers repeatedly over 10 seconds. If I do that with a traditional GDB setup, I am throwing the CPU into debug halt states, I'm stepping through memory, and I am completely destroying the real-time execution of the chip.
Right, you trigger the observer effect.
Exactly, the observer effect. The act of measuring the timing destroys the timing. If you have an I2C bus error that only happens when a race condition hits a 1 millisecond window, the moment you attach a debugger and pause the core to read the memory, the race condition disappears. The bug just hides from you. So how does Analyse Prog suck all this data out of the chip without causing the thermometer display to flicker or the timer to miss a pulse?
This is where we have to talk about the physical physics of the ARM debug architecture. Specifically, something called the AHBAP, the Advanced High Performance Bus Access Port.
Break that down for us. How does the AHBAP solve the observer effect?
In older, simpler microcontrollers, if the debug probe wanted to read memory, it had to interrupt the CPU. It would inject an instruction into the pipeline, force the CPU to physically read the memory address, and then have the CPU spit the data back out to the probe.
Which ruins the timing, because the CPU has to stop running your actual code to go fetch your debug data.
Exactly. It's incredibly invasive. But modern ARM Cortex chips utilize a dual-ported memory matrix. The AHBAP is a dedicated hardware module that sits on the main internal bus, completely parallel to the Cortex CPU core. When Regmon 2.0.0 sends a memory read request over the SWD wires, that request hits the AHBAP.
Okay, so it goes to this parallel module.
Right, and then the AHBAP directly accesses the peripheral memory space, or the SRAM, grabs the data, and sends it back out the SWD wire. The CPU isn't involved at all.
Wait. If the AHBAP is accessing the exact same memory matrix the CPU is using, isn't there bus contention? Does the CPU get stalled waiting for the debug port to finish its read?
It's an excellent question, and it highlights the beauty of the ARM bus matrix. The matrix allows multiple bus masters to operate simultaneously. Unless the CPU and the AHBAP try to access the exact same memory bank on the exact same clock cycle, there is zero contention.
And if they do collide.
Even if they do hit the exact same bank at the same time, the stall is typically a single clock cycle. We're talking a fraction of a microsecond.
So it's completely imperceptible to the running firmware.
It is absolute zero interference, non-invasive inspection. The Cortex core is executing its C code, running down the highway at 80 megahertz, completely oblivious to the fact that the AHB AP is flying alongside it, continuously reading the peripheral states and streaming them back to Regmon. Your timers keep ticking, your interrupts keep firing, and your race conditions still happen in real time.
You can actually watch the bug happen naturally in the wild. I mean, that is the holy grail for embedded engineers. Okay, so Analyse Prog gives us a perfect, real-time topographical map of what the hardware is doing. But this brings me to a forensic problem.
What's that?
What if the hardware is doing exactly what it was told to do flawlessly, but it was told to do the wrong thing?
The logic bug versus the hardware bug.
Right. The registers look perfect, the SPI bus is transmitting beautifully, but the display is still rendering garbage because the actual payload data in memory is corrupted, or maybe you accidentally flashed an old version of the binary. The dynamic hardware map won't catch that.
And this is exactly why non-invasive debugging can't solely rely on live peripheral mapping. You have to be able to inspect the static payload, the actual binary living in the flash memory. Which brings us to the fourth major feature, the strings tool.
Strings. That is a very familiar name for anyone who has lived in a Unix or Linux command line environment.
It's a classic forensic utility, and bringing it to the microcontroller debug workflow is honestly a stroke of genius. The strings feature in Regmon 2.0.0 bypasses the peripherals entirely and initiates a deep, sequential scan of the chip's internal flash memory.
Flash memory being where the compiled application code is permanently stored, which usually starts around memory address 0x080000 on an STM32, right?
Correct. The tool iterates through the flash memory over the SWD link, byte by byte, and performs pattern matching. It's looking for continuous sequences of ASCII characters, specifically ranges from 0x0 by 2x7e that are terminated by a null byte.
So it's essentially hunting for readable English words and phrases buried inside the compiled hexadecimal machine code.
Exactly. It extracts every plaintext artifact it can find in the row data sections of the binary and just prints them to the console.
Now, a junior developer might think, well, it's compiled C code, there shouldn't be any plain text in there at all. But firmware is absolutely littered with human-readable clues, isn't it?
Oh, it is a gold mine for forensics. Compilers leave incredible amounts of metadata in Flash. You'll find assertion failure messages, hard-coded file paths from the build machine, HTTP headers if it's an IoT device, verbose error strings, ASCII art boot banners, and copyright notices.
It's the equivalent of finding the manufacturer's handwritten QA notes stuffed inside the door panel of a car.
Precisely. And in a chaotic prototyping environment, scanning the flash for these strings gives you undeniable physical proof of what is truly living on the silicon, rather than what your IDE claims it just flashed.
There is an incredible anecdote from the field reports that perfectly highlights this, involving a developer named Terry and a deeply confusing board.
Ah, yes, the McCrisp Stellaris anomaly. It is the perfect case study for this exact forensic workflow.
Walk us through it. Set the scene. Terry has a board on his bench. It's supposed to be running a specific, newly written C program, but it's failing in highly erratic, totally unpredictable ways. He checks the compiler, he checks his wiring, everything seems correct, but the chip is just acting haunted.
Right, so he turns to Regmon 2.0.0 and initiates the strings tool to dump the flash artifacts. The tool scans the memory, and among all the standard C libraries you'd expect to see, it spits out a completely unexpected plain text string. It finds the boot banner for a language environment called McCrisp Stellaris.
Which is a fourth language runtime?
Yes, an entirely different programming language just sitting there dormant in the flash memory.
That is wild. Imagine compiling a massive C++ project, searching the binary, and finding a chapter of a Python script randomly injected into the middle of it. It's totally jarring. But wait. How did it get there? Did the C compiler hallucinate it?
No, it's a symptom of how flash memory architectures actually work. Flash memory is divided into large sectors, sometimes 16 kilobytes or larger per sector. When a flash tool writes a new program, to save time, it often only erases and overwrites the specific sectors required for the new binary.
Ah. So if Terry had previously flashed a massive fourth environment onto this board, say, a month ago, and then today he flashed a tiny C program.
The flash tool only erased the first sector to make room for the C code. The rest of the fourth environment was left completely untouched in the higher memory addresses.
So the chip is carrying around the ghost of a previous project, but here's the crucial question for the actual diagnostic process. Did finding that fourth banner solve the bug? Was the ghost code somehow executing and ruining the C program?
No. And this is where the integration of these tools proves its real worth. Finding the fourth banner was technically a red herring in terms of execution, but it was the catalyst that shifted Terry's mindset. It proved to him that he didn't actually know what was on the chip. It forced him to stop assuming and start verifying the hardware's truth.
So how did he integrate the suite to isolate the actual problem?
It's a three-step forensic methodology. Step 1. He used detect chip to ensure he had the absolute correct SVD map for the exact silicon revision. No more guessing. Step 2. He used the strings discovery to confirm that his flash memory was fragmented and potentially untrustworthy. Step 3. Because the flash was suspect, he abandoned static analysis entirely and ran Analyse Prog to look at the dynamic live execution.
And what did that live hardware map reveal?
Analyse Prog observed the AHB and APB buses, sampled the peripherals, and mathematically proved that the hardware was being configured exactly the way the C code intended. The timers were running at the correct prescalers, the GPIOs were in the correct alternate function modes.
Which means the C code was executing correctly. The ghost fourth code wasn't interfering at all.
Exactly. The hardware was doing exactly what it was told. By proving that the silicon was healthy and the configuration was executing properly, it completely eliminated hardware failure, compiler bugs, and flash corruption from the suspect list.
It pointed a giant neon sign at Terry's own logic.
It did. It forced him to look deeper into his own algorithmic logic in the C code, where he eventually found a simple, hidden arithmetic error. The tools didn't fix the bug for him, but they provided the absolute proof necessary to stop the engineer from chasing ghosts in the hardware.
That is forensic engineering at its absolute finest. But I want to pause here and talk about the user experience of actually running these deep scan operations. Because scanning megabytes of flash memory over a relatively slow 4 megahertz SWD clock, or mapping the entire dynamic state of every peripheral, that is not instantaneous.
No, it is highly computationally and bandwidth intensive.
And as any engineer will tell you, there is nothing more anxiety-inducing than clicking a button in a debug console, having the UI freeze, and just sitting there in silence. You don't know if the USB handle crashed, if the ST-Link locked up, if the AHB is stalled, or if the tool is just thinking. If I sit there for 10 seconds with a frozen screen, my instinct is to yank the USB cable out, which is the absolute worst thing you can do because it can lock the debug port entirely.
Oh yeah, never pull the cable. The developers recognized this psychological friction, and they implemented a very elegant, albeit simple, UX solution: status bar percentage indicators.
Just a standard progress bar.
Yes, but in the context of hardware polling, it's critical. When you initiate strings or Analyse Prog, the Regmon console immediately populates a status bar at the bottom of the terminal, actively counting up 5%, 10%, 15% as the SWD packets are processed.
It's the heartbeat of the tool itself.
Exactly. It gracefully manages user expectations. It provides immediate visual confirmation that the Libus connection is healthy, the SWD clock is ticking, and the CPU is responding. It allows the engineer to initiate a massive forensic scan, visually confirm it's running, and then context switch to another task, trusting that the tool hasn't hung.
It's a small detail, but in a high-stress debugging scenario, knowing you don't have to restart your entire tool chain is massive. Okay, so we've mapped the chip, we've analyzed the live registers, we've mind-read the architecture, and we've dumped the flash forensics. We have an incredibly powerful workbench.
A complete diagnostic suite, really.
But here is the reality of embedded development. Diagnosing the bug is only half the battle. The other half is actually writing the fix, flashing it to the chip, and testing it. And historically, the plumbing required to do this has been incredibly painful. Which brings us to a critical workflow revolution in Regmon 2.0.0. We need to talk about the SWDD daemon, the fundamental conflict over USB access, and the stark difference between traditional C development and the fourth iterative workflow.
This is where we look at the infrastructure that actually allows these tools to talk to the silicon. And the core of that infrastructure is the SWDD daemon, authored by a developer known as Crest.
Let's define the architecture here for everyone listening. You have your PC running Regmon, you have a USB cable going to a hardware probe, like an ST-Link, and you have the two SWD wires going from the probe to the silicon. Where does the SWDD daemon sit in all of this?
The SWDD daemon is a background process running natively on your PC. It acts as the exclusive bridge operator between the software tools and the physical USB hardware. Its entire job is to claim the USB interface of the ST-Link, hold that connection permanently open, and translate high-level requests from Regmon into low-level SWD wire protocols.
Okay, so it's basically a multiplexer for the debug link. That sounds great. What's the problem?
The problem is a fundamental limitation of modern operating systems, specifically how libraries like libusbub handle device access. To guarantee data integrity, When the SWDD daemon claims the ST link, it takes an exclusive lock on that USB endpoint.
Right, so no other software on your PC can talk to the ST-Link.
Exactly. But when you write a new C program, you need to compile it into a .bin or .hex file, and then you have to use a completely separate piece of software, a flash utility like OpenOCD or SevFlash, to physically burn that binary into the chip's flash memory.
And what does the flash utility need?
It needs the exact same ST-Link USB endpoint.
Ugh. A resource collision. The flash tool and the daemon are in a street fight over the same piece of hardware.
And it is a catastrophic fight. If the SWDD daemon is running, holding the port open so Regmon can monitor registers, and you try to run your flash tool, the flash tool just gets an access denied error from the operating system. It crashes, the flash fails, and your workflow comes to a grinding halt.
This sounds miserable. Walk me through the actual human workflow for a C developer dealing with this in older environments.
It is the definition of friction. You are in your IDE writing C code. You hit a point where you want to test. First, you have to tab over to a terminal window and explicitly kill the SWDD daemon process to release the USB lock.
You literally have to manually evict the bridge operator.
Yes, the moment you kill it, your Regmon console loses its connection and likely throws a massive error. Now the port is free. You tab back to your IDE, invoke the flash tool, wait for it to erase and write the flash, and then the flash tool releases the port.
Okay, the new code is on the silicon.
But now you are flying blind again. So you tab back to the terminal, restart the SWDD daemon, tab back to Regmon, reestablish the connection, and finally look at your registers. You see that your new code didn't fix the bug. So you have to write a new line of code and repeat the entire agonizing sequence. Kill daemon, flash, start daemon, connect, test.
Stop, flash, start, test. Over and over. It's a massive context switch just to test a single variable change. It completely destroys any chance of maintaining a flow state.
It is incredibly disruptive. But here's the fascinating twist. While C developers have suffered through this start-stop friction for decades, developers using interactive languages like Forth, specifically that Mecrisp Solaris environment we discussed earlier, have a completely different experience.
Right, because the whole philosophy of Forth is that it runs live on the silicon. You have a REPL, a read evil print loop. You type a new hardware command into your terminal, it goes down the wire, compiles into Flash instantly, and executes live. You are basically constantly chatting with the chip.
Yes, the Forth workflow is built entirely on rapid millisecond-level iteration.
So, wait a minute. If the Forth environment is constantly sending new code down to the chip to be compiled, and Regmon is constantly pulling live register data back up from the chip, how are they not colliding? Why doesn't the Forth system crash into the SWDD daemon's USB lock?
This is where Crest, the author of SWDD, implemented a truly brilliant piece of computer science. To enable that seamless interactive workflow, Crest built a mechanism into the daemon called a synchronized cache.
Okay, let's unpack the synchronized cache, break down the architecture for me.
Okay.
How do you bypass a hard USB lock?
You bypass the lock by not fighting over the USB endpoint at all. Instead of having two separate PC programs trying to shove data down the USB pipe, Crest moved the communication layer into the silicon's RAM.
Into the microcontroller's memory.
Yes, they established a dedicated shared memory region, a lock-free ring buffer inside the microcontroller's RAM.
A drop zone.
It's exactly a mailbox. When the Forth runtime on the silicon wants to print a debug string to your PC console, it doesn't try to initiate a complex USB transfer. It just uses a standard CPU instruction to write those ASCII bytes into that specific memory address in its own RAM.
Okay, that takes nanoseconds for the Cortex core.
Meanwhile, the SWDD daemon on your PC, which already holds the exclusive USB lock, is continuously using the AHB-EP debug port we talked about earlier to quietly peek into that exact memory address.
It's just silently pulling the mailbox.
Right. And when the daemon sees new data appear in the ring buffer, it pulls it over the SWD wire and routes it to the Forth terminal window on your PC. And the flow works perfectly in reverse, too. When you take a new Forth command on your keyboard, the SWD daemon gently writes those bytes directly into the chip's RAM via the debug port, and the Forth runtime picks it up.
That is staggeringly elegant. Because it leverages the AHB-AP, the read-write operations happen completely independently of the CPU's main execution.
It is a gentle, continuous exchange of memory states. It is not a hostile takeover of the entire chip like a standard C flash utility requires. The SWDD daemon synchronizes the traffic. Regmon can be aggressively polling the RCC registers for Analyse Prog, while the Forth terminal is simultaneously reading and writing to the SRAM mailbox, and the daemon routes all of it seamlessly over a single, unified USB lock.
Neither side waits, neither side crashes. It effectively multiplexes the debug link at the memory level. I see why Forth developers love this, but this brings me back to the C developers. They aren't running an interactive REPL. They are still compiling massive .bin files that require a hard reset and a dedicated flash loader. Are they just doomed to the terminal-killing, context-switching nightmare forever?
Not with Regmon 2.0.0. The developers recognized the pain of the C workflow and brought the daemon management directly into the graphical interface, solving the friction with profound simplicity.
How exactly did they integrate it?
They placed two highly visible buttons at the very bottom of the Regmon console, SWDDD on and SWDDD OFF.
Just a toggle switch.
It's a toggle, but it is deeply integrated with the daemon's API, and it features a brilliant piece of visual feedback to manage the state machine. Each button contains a status indicator block. A solid block represents the active, true state of the daemon, while an outline represents the inactive state.
So there's no ambiguity. You don't have to guess if the daemon is currently holding the USB lock. You have a clear, absolute guide for managing the daemon status right in your eyeline.
Exactly. So let's contrast the new C workflow against the old nightmare we described. You are writing your C code. You are ready to test. You do not leave the Regmon window. You simply click SWDDOFF.
And what happens under the hood?
The UI sends a signal to the daemon telling it to gracefully drop the libuzz block on the ST link.
Now, in older software, dropping the connection abruptly would cause a cascade of error pop-ups, stack traces, and a completely frozen UI. How does Regmon handle it?
With graceful degradation. The UI updates instantly, but it doesn't crash. All of the live hexadecimal register values on your screen smoothly transition into dashes.
What's dashes?
Just dashes. It is an honest, quiet reporting of the hardware state. It tells the engineer, I have willingly relinquished the port. I have no live data to show you, so I will show you nothing.
No panic. Okay, so the port is free.
The port is completely free. You click a single button in your IDE to invoke your flash tool. It grabs the uncontended USB port, writes your new C firmware in 3 seconds, and releases it.
And then?
You look back at Regmon and click SWDD on N. The daemon instantly reacquires the USB lock, initializes the AHB AP, and the live register values flood back onto the screen, replacing the dashes in real time.
That is a total workflow revolution for iterative firmware development. It takes the most fiddly, error-prone, frustrating part of the C development cycle, the constant terminal context switching, and reduces it to 2 clicks and a glance at a UI. Right, click OFF, flash, click on N, observe.
It keeps the developer in the flow state. It reduces the friction of interacting with the physical silicon to almost zero. And when you step back and look at the aggregate of all these features, the automated mapping, the dynamic time series analysis, the architectural mind reading, the forensic memory scanning, and the frictionless workflow, what's truly staggering is the accessibility of this power.
That is an incredibly important point to emphasize, because when you describe non-invasive silicon inspection and AHB, AP bus matrix profiling, it sounds like you are describing a multi-million-dollar capability.
Historically, it was. If you wanted to do this level of deep hardware profiling 10 years ago, you were buying proprietary logic analyzers and licensed debuggers from massive silicon vendors. You were spending $5,000, $10,000, maybe $20,000 per seat. You were locked into their specific ecosystem, and you had to sign NDAs just to get the documentation.
But look at the reality of Regmon 2.0.0.
Regmon is a free open-source tool. It runs natively on a standard everyday Linux or Windows PC. It communicates through a generic ST-Link debug probe that you can purchase from any electronics distributor for literally $3 or $4. And it is interrogating ARM microcontrollers that cost less than a cup of coffee.
It is the absolute pure democratization of hardware debugging. It brings forensic diagnostic power that used to be reserved for enterprise labs directly to the workbench of any student, hobbyist, or professional with a laptop and a curiosity about how silicon actually functions.
It really is a paradigm shift in how we relate to the hardware.
Let's summarize this massive leap for everyone, because the delta between where we started and where we are now is vast. Version 1.0 was a solid tool. It let you read the dashboard of the chip, but it required you to trust your own flawed memory about which dashboard you were looking at.
It was blind trust.
Right. But version 2.0.0 replaces human assumption with hard hardware evidence. It automatically detects which dashboard you have by interrogating the physical ID code, ensuring you never look at the wrong SVD map again.
It ends the guessing game at the physical layer.
Then it doesn't just read the dials. It uses Analyse Reg to sample them continuously, turning static snapshots into dynamic time series data to catch silent errors and timing issues.
It reveals the kinetic motion of the peripherals.
And it scales that up to absolute mind-reading levels with Analyse Prog. By traversing the RCC and the AHB bus matrix, it maps the entire engine's logic without ever needing the source code blueprints. And because it leverages the AHB AP debug port, it does it all with zero interference, completely avoiding the observer effect.
Reconstructing the software intent directly from the hardware exhaust.
Then, for forensic proof, you have the strings tool, which scans the raw flash memory to uncover hidden manufacturer notes and rogue compiler artifacts, letting you integrate dynamic analysis with static payloads to solve impossible bugs like the Mechrist Solaris anomaly.
It separates the logic bugs from the hardware faults with undeniable proof.
And finally, it glues it all together with a frictionless workflow. Whether you're utilizing the synchronized cache for real-time fourth iteration or the new SWDD UI toggles for rapid C flashing, it lets you swap out the engine parts without ever breaking your tools.
It fundamentally changes the diagnostic landscape, from guessing in the dark to knowing with absolute certainty. The silicon never lies. Regmon just gives you the vocabulary to ask it the right questions and the bandwidth to actually hear the answers.
Which leaves us with a final, slightly provocative thought to mull over. Embedded engineering has always relied on the concept of the black box. You compile your proprietary C code into a stripped binary, you flash it to the microcontroller, you lock the readout protection, and you assume your intellectual property is safe because no one can read the source code.
That has been the foundational security model for decades.
But if an open source piece of software running through a $3 debug wire can now use AI to completely reconstruct the macroscopic architecture, the timing, and the behavioral intent of a compiled program in real time without ever touching the original source files.
It raises a profound question about the viability of hardware obfuscation.
Exactly. What does this mean for the future of proprietary firmware security? We rely on binary compilation to hide how things work. But if the physical silicon itself cannot help but radiate the absolute truth of its operations to anyone who knows how to listen on the bus matrix, is the very concept of a closed system in embedded hardware fundamentally obsolete.
That is something every hardware manufacturer, from consumer IoT to industrial automation, is going to have to think long and hard about as these tools become more prevalent.
Something to keep you awake at night the next time you look at the blinking LED on a smart thermostat and wonder what it's really doing. Thanks for joining us on this deep dive. See you next time.